welcome to lecture number 25. So, we have been discussing about the Kepler's equation and we used standard integration to solve this problem also, and in a normal process also by doing various steps we have also worked out. So, today again we are going to look into the ellipse problem, and it is a different way of looking at the same problem, and if you are aware of these different ways, so then it will help you in solving various problems. So, let us look into this ellipse. So, we have an ellipse here, and then there is a circumscribing circle which we have named as auxiliary circle. We take the focus here in this place. This is your R and this angle is theta. So, this angle is theta and this is R to this place. From here we drop a perpendicular and extend it upward wherever it cuts. So, this point we have named as M, this point we have named as N, this is your focus, and then we connected the center of the ellipse, and this angle we have written as E, which is eccentric anomaly, and this point we write as C. So, C n, this becomes, and this is obviously A, the radius of the circle, which is nothing but this quantity, this is also your A semi major axis. So, C n equal to A cos E, C n equal to A cos E, and this quantity will be equal to, from here to here, this distance is A E, and this distance is R cos theta. So, C n equal to A cos E equal to C f plus F n, and then we can write C f as A E plus R cos theta, this equal to A cos E, and then we replace this by L by 1 plus E cos theta, and this is L cos theta. One more step we need to do here. These relations we are aware of, so we utilize them, and this implies cos E will be equal to E plus A cancels out from both the side, 1 minus C a square cos theta divided by 1 plus E cos theta, and therefore, cos E, this can be reduced to E plus E a square cos theta plus cos theta minus E a square cos theta divided by 1 plus E cos theta, and this implies cos E equal to E plus cos theta divided by 1 plus E cos theta. So, we have derived this relationship earlier also, but we have done it in a different way, and if we rearrange this, rearranging this gives us cos E plus E cos E times cos theta to E plus cos theta. Cos theta, if we bring it on one side, so 1 minus E cos E times cos theta cos E minus E, and this implies cos theta equal to cos E minus E divided by 1 minus E cos E. So, here this is your cos E and this is cos theta, which we have worked out earlier also, but there we use this as information that m n divided by p n, this will be a by b, it is in this ratio. Okay. And based on that, then we worked out all the relations, but here also you can proceed in this way. It is a little longer, but it is a you get the same result. Okay, so, we have got here cos E and cos theta, and therefore, sin theta and cos E sin E can also be computed using these two relations. Sin E can be written as 1 minus cos square E and this is the reason I have not taken it earlier in the conic section, because discussing at a time when we need it, it is much better. If you simplify it, so you are going to get the equation sin theta. This step I am leaving to you. And therefore, sin E is sin theta times 1 minus E square under root divided by 1 plus E cos theta. Okay, so, this is one equation, this is another equation. Here we have the sin E, and the same way cos E already we have used. See here also we write it properly. This is cos square E. Okay, cos theta is also given. So, in the same way sin theta can be obtained. So, sin theta, this equal to 1 minus cos square theta under root, and insert the value for the cos theta. Cos theta is E plus cos E minus E, cos capital E minus E, and then 1 minus E cos E, 1 minus E cos E, this whole square under root. And if you simplify it, again I am writing the final result here to save some time. So, this way you can proceed to solve the problem of the ellipse. Once you know all these things, so rest of the procedures we have carried out, it remains the same. If the rest of the procedures remain the same. So, we do not need to elaborate that, but what I was trying to show here, that how sin E and cos E sin theta cos theta, they can be written in terms of each other. Okay. Therefore, based on this you can write the relationship for R also, which I am not going to do, because it will be mere repetition what we have done earlier. So, we skip that step here in this place. Okay. Next we have the case of hyperbola. Hyperbolic orbit. For this we want to derive Kepler's equation. So, what form this will be? So, obviously, we have written one standard integration. So, using that we can work it out, which we have written here in this place. This is your standard integration for hyperbola. So, if we utilize it, we can work out the problem. So, we do this, and thereafter we will do it by some other method, which will be quite interesting to look into. Okay. So, we will finish this part and then go into the next step. So, for the case of hyperbola, we have d theta this quantity will be now. Here in this case, what we are doing, if we go back here in this equation, we are using this equation. Okay. So, beta we are writing as E and alpha we will write as 1. Okay. So, therefore, here in this case you can see that alpha is less than beta. So, that means 1 is less than E. Okay. So, this information we are going to utilize. So, looking into this part, so only this particular part we are writing currently. So, this gets reduced to E times, replacing everywhere beta by E and alpha by 1. And these equations will be very useful later on while doing the trajectory transfer problem. Okay. So, now we have t minus t this quantity times h square, h divided by L square, h divided by L square this equal to d theta by 1 plus E cos theta whole square, and this is between 0 to theta we have written. Either we can write from theta 0 to theta, it is not a problem. So, in that case only the boundary will change, you will write here theta 0, upside you will write theta. Okay. this is the only change then we will do here. So, here you can write this as theta 0 and theta. So, this term is available to us. So, 1 by E square minus 1 to the power 3 by 2 and rest of the terms which will get copied from this place to this place. Now, left hand side then gets reduced to and the right hand side again we copy this whole thing here. Okay, if we reduce the left hand side, so we are interested in eliminating h here. So, we write here mu by L under root L square E square minus 1 to the power 3 by 2 and this quantity will be t minus t mu times a cube under root and this equal to on the right hand side this whole thing copied here. Okay. So, I will copy here, let us say E times E square minus 1 under root sin theta So, mu by a cube here a, remember a here in this case which is appearing a is greater than 0, this is greater than 0, in this place a is appearing. So, this quantity a is greater than 0. Where we have used the information L equal to a times L times L equal to a times E square minus 1. Okay, so, this way this problem is also solved and here we write m, this is the mean anomaly and on the right hand side this whole thing is to be copied. So, better we write here in this place itself m equal to rather than copying one more step and wasting time here. So, we skip that step. Okay. So, this is your solution. Your solution is here m equal to m this equal to finally this quantity here. Now, I will take you to some different way of doing the problem and that too in the Kepler's equation form we will write. Okay. And see the most important thing that I am going to write here, that either you write this way or write this way, both are valid for hyperbola. This is your semi latus rectum and this is semi major axis and this is eccentricity, both are valid, but here in this case a is less than 0, here in this case a is greater than 0. So, say this if I write it as minus a times E square minus 1. Okay, so, you can see that this quantity L is a positive quantity. So, here minus a this should be a positive quantity, that means A is less than 0. Here in this part A appears as less than 0, but here A is greater than 0. So, these are the two ways of writing the same thing. So, now what our objective is to derive the Kepler's equation for hyperbolic orbit, where it is given that r equal to a times 1 minus e cos hyperbolic f. Again, here I would like to point out, and I will write it in red, that I can also write this as e cos hyperbolic f minus 1. This is another way of writing. R is always greater than 0. R is always greater than 0. Here in this case A is greater than 0, here in this case A is less than 0. This is the difference of representation, and both are valid. As you can see here in this place, if I rewrite this equation as e cos hyperbolic f minus 1 minus n, if I put it here, and then you can see if I write this as a prime. So, e cos hyperbolic f minus 1. So, this is not it this a prime, I can write this as greater than 0, assuming here because the a is less than 0. So, this gets reduced into this format. You can see that both are the same then. Okay. So, we are going to use this equation, and what we have to prove, that for the hyperbola the Kepler's equation, this can be written as n times t minus t, this equal to f minus e sin hyperbolic f, where f is here, just like we have the eccentric anomaly for ellipse, the same way this is eccentric anomaly for hyperbola. And what this quantity is right now, do not worry, we will take up this issue later on. Okay. And here the quantity n is minus a cube minus mu by a cube under root, because t becomes equal to this is mu by minus a cube. Okay. So, on the left hand side, then we write this as the mean anomaly for hyperbolic orbit, MH is mean anomaly for hyperbolic orbit. So, we are not considering then this equation, we will work with this. You can also work with that, there is no problem. There are actually so many issues while discussing all these problems, like in the case of ellipse, if you remember that for deriving this b, this is your b, this particular part from here to here, semi major axis. we took this angle and then we worked in a particular way. It was a long way of working obviously, but that could have been done in a very short way also. Purposefully I followed that path because that was more generalized. Say here in this case we always know that in the case of ellipse, this distance from here to here plus here to here or to any other place from this place to this place, this is always 2a. That means, if I write this as p, so p f star plus p f equal to 2a, which we have discussed in the case of conic section. Okay. So, once we take the minor axis, so in that place this becomes a and this becomes a. And this distance, we know this distance is a. So, therefore, b then in that case becomes a square minus a square e square under root. So, this is a times 1 minus e square under root. So, this is so straightforward, okay, but we took a generalized way of doing in conic section while discussing the conic section. Okay. That was good, because it was independent of this information that we are using here, that this length and this length, they are equal to a, we did not use there. Okay. So, let us forget this and return back to what we are interested in doing here. So, our objective is to use this equation and prove that the mean anomaly for the hyperbolic orbit, which is m h, it is given by this particular equation. So, we start with r equal to a times 1 minus e cos hyperbolic f. This is the angular momentum per unit mass. Okay, this we have done earlier. So, I have written here quickly. R dot v already we have also worked out, again writing here. The symbols have their usual meaning. This unit vector E r cap, unit vector in the direction of the radius vector, and E theta is cap is perpendicular to that E r cap. So, this gets reduced to, and there is a dot product here. So, this is r times r dot. So, therefore, this equation gets reduced to now we take r equal to a times 1 minus e cos hyperbolic f So, r dot will be equal to minus a times E sin hyperbolic f, where this hyperbolic function you may be aware of. I presume that you are aware of all these things. Cos hyperbolic f is e to the power f plus e to the power minus f divided by 2, and sin hyperbolic f minus. So, if you differentiate cos hyperbolic f, you will get sin hyperbolic f. So, we have here r dot, and together with f dot will come here. Now, we insert this, let us say this is equation A and this is equation A, this is equation B, and this is equation C. So, we insert equation C into equation B. So, A and B, they will be inserted in equation B. H square, this is nothing but mu times L. You remember that from the conic section we got this expression H square equal to mu times L, and while working out the expression for the conic section, we did not assume anywhere that whether it is a hyperbolic, it is a parabolic, or it is a elliptic. Irrespective of that, this is valid. Okay. So, therefore, we replace H square by mu times L, and this mu times L we write as 1 minus E square. So, again remember we are not using this expression L equal to A times E square minus 1. If I use this, means I am assuming here A greater than 0. If I write L equal to A times 1 minus E square, so here we assume A is less than 0. So, I am using this part, okay, not this part. So, using this, then we can write mu A times 1 minus E square, this equal to r square V square minus r r dot square Now, V square also in the central force motion, what we have seen that the equation we derived for the energy we derived this equation. Okay. So, if you take A is positive, this is for ellipse. If A is negative, then it becomes hyperbola. If A is infinity, it becomes parabola. But it is not necessary. See, anywhere if I write like here in this case, if I write like this. So, here we know that A is negative for the hyperbola, the semi major axis. But if we are writing here in this fashion, so we are just putting the magnitude of A, not the sign, while here in this case we insert along with the sign. Okay, this is the difference here. So, we utilize this equation here in this place. So, from here what we see that V square by 2 plus mu by 2 A, this will be equal to mu by r. Okay, so, what we need to replace here, this is the quantity V square. Okay, not the other way, what we have written here, we need to replace this V square. So, we write it here V square by 2 equal to mu by r minus mu by 2 A So, here r square times mu by r minus mu by 2 a. So, again see I am not putting the here earlier I have told you that for the hyperbola v square by 2 minus mu by r equal to plus mu by 2 a. So, there we assume that a is greater than 0, this is for hyperbola. But if we go with this minus sign, so in this place we will assume that a is less than 0, only then this is valid, otherwise this will become invalid. So, we continue with this expression. So, here what we are assuming that a is less than 0. Under these circumstances we are this condition we are working here. And this is v square by 2. So, this will get multiplied by 2 here in this place minus r times r dot square, and of course, once we break the bracket. So, this becomes mu r 2 mu r, and here minus 2 cancels out, and this is mu r square divided by a minus r r dot square. This is your h square. Okay, so, we will complete it in the next lecture. Thank you very much. So, we have achieved till a point where now it is easy to work out this problem. Again we will continue in the next lecture. Thank you.